a one-dimensional submodel. And I can tell you this now is just that G1, where I took the P to give you the first prime after 592,000, which is 592,000 and 19. So I guess this is number here. So the second one is your n is just a power of some prime at the f star of G, the center of G, time an extra span group, I mean R group, and then the sim n of B contains a one-dimensional submodel. And the third case is when your G is almost square simple. Okay, so then what do I have here? Okay, so and V restricted to the layer G is irreducible, and sim K V contains a one-dimensional submodel. So when your K is something like 10n divided by 31, something like that. Anyway, and so I can tell you how do I prove that one of these cases occurs. Well, for the first case, then I use the Rototom theorem. For the second case, I'm going to use the this case right here. So this is the proposition 1, the second case. And for the third case, I want to use the proposition 1 in the first case, where on the gamma is 0.99. So gamma is something well less than 1, is very close to 1, but the main thing is still less than 1. So where does this 0.99 come from? So let me remind you that what is gamma. So I want the gamma so that the Cantor ratio is bounded by gamma, right? Okay. Right. So I think now I can erase this. Okay. So why can I take gamma to be why gamma can be equal to 0.99. So there's a great result into Leibniz and Kayhata. We say that if your G is square simple and not AN, not the alternating group, and then for any non-standard element, and for any pi, then you can show that type G over type 1 is bounded by 0.95. This 0.99 is a bigger. And this is because I want to know this only one square simple, not just square simple one. So if you take this result and use a lemma into walk run it, and myself that we did is 0.99 for only one square simple. Yes.
If you assume G is simple, can you do maybe a lot better than zero?
Not really. I think that was theoretical, right? No one created that previously when we
There's like a controlled family of examples that are bad, or it's really generic.
Yeah, right. So if you look at the papers, some papers they do then you can see where the back can come from. Yeah. Right. Of course, you can ask me. So what do you do proving this again before the again, then we have to do some special argument. And at this point, he did use a random to quadratic and Michael Larsen. Okay. But anyway, so we can go back on the end and we see the 0.99 classes for us. So for the purposes of proving the total conjecture, then this bound was perfect. Okay. And in fact, there are many papers using this bound of David Luck and Kai Marker. So can we improve on the bound on this bound 195? Well, if you open the atlas and you look at the current table, I think the one thing that Percy Diaconis keeps telling us, well, you see that if you look at the, how does he say? Okay, so I'm doing two sections the wrong way, but anyway, so if your element is far from being central, then the character ratio is going to be very small. And so how do you quantify that in a statement? So, well, okay. So let me just collect one result. So suppose that U is a class move on a W. So W is going to be finite a vector space or finite field. So let me define maybe SNW or SPW, right? Then I'm going to define the support of your G to be the codimension of the largest ideal space. So I look at all the lambda in the F2 bar, and I look at the codimension of the current G minus lambda. Okay, and it is a theorem due to Michael Larsen and Charlotte. And well, we say that in this case, you can show that the chi G over chi 1, we can bound it, you can bound it better than this. So it's going to be bounded by 1 divided by Q to the square root of the support of G divided by 151, something like that. So if your Q is large enough, if your support is large enough, and if it's fine, you can go to something very small. But the point is, this bound is a little bit better than this bound in some cases, but for some other application that you have to study, we need something much better. Okay, so what we really need is the following. We need some exponential bound. So our dream is to have the following bound, to have exponential bound like this. So it's going to be for only G in our group. Probably I have to say this would be a symbol. So based on alpha, which is alpha G, between 0 and 1, and I want it to be as small as possible. As small and also explicit as possible. Okay. So that on the chi, then chi G is going to be bounded by chi 1. Power. Okay, so why do you want to practice the thing? So this one application. So let's say that I want to study the missing time in random walk. And why? Well, let me say it's a lemma. So let's assume that your G is equal. And suppose they have a quantity class of some element G. which is real. So it means it's also going to take the G inverse, just to make things simpler. And suppose that I have this alpha here. Okay. Then, and let's, okay, so let me say. So let's consider the random walk on the K graph of G with respect to this class K. So it means that the vertices of this graph are going to be the element in the group, and the edges they are given by the convex of your G. And the graph is undirected because the class is real. Okay. Then if the order G is large enough, then the missing time of this random walk is going to be for TGK. This is just the notation for this missing time is going to be at most 1.6 divided by 1 minus alpha. Okay. And the proof is really easy, but I just want to mention one thing. So the proof is a surprise that today we only heard the name of the 2 times. So let me mention the name. I mean this name one more time. So we use the rhythm zeta function. So zeta of G of S, zeta sub G of S is going to be the sum of the reciprocal of chi 1 to the S power when chi is any illusion factor of G. And then the basic result that we can prove about this zeta function is due to Martin-Dirac and Hannah. This shows that if you look at the zeta function of G at something larger than 1, so let me say 1.2, then this will be 10 to 1 when the order G can to infinity, G is simple. So you can see that my 1.6 is just 2 plus 1.2 divided by 2. Okay. So this is one application. Okay. And there are some other applications that we would like to solve using counterbound. So the second one, we also want to study the finite function of function or any one. We have to look at one particular case. Obviously, there are some other applications that we want to study the so-called representation varieties. So do we have this kind of bound, the exponential one? So do we have exponential bound? Well, so the first case that we have such a bound is a case of when your G is symmetrical. And it was proved by survey forming and ruler in 1998. To show that if your G is in Sn and is homogeneous, so meaning it is a product of n cycle only, then you take alpha G to be something like 1 over n. But I have to say that this result is asymptotic, meaning it's only true when your n is large enough. And 10 years later, Michael Larsen and Andy Charlotte, they prove it for any commutation. But again, the result is asymptotic, and also alpha T is kind of implicit. So it's not easy to calculate the alpha G. So our main case is that with the group of Lie type, of course for this polynomial, then we know only calculation, so we can work out the alpha. So what about Lie type group? Okay, so here's the theorem B, which is due to Paraman Vedrunkanka. So this theorem is kind of long to formulate, so let me put it in the right way. Okay, so this is a function f of n to n, and we measure number with the following property. So for any semi-simple, so I think that I will assume that G is kinetic reductive. For any kinetic reductive under the group, say if G in group characteristic, or any homogeneous map on G, of course I'm guessing that the rank of the semi-simple rank of G is going to be R, right, and for any G in the finite group, I will want G and F, such that the centralizer of the G is 1 with Levy. What does it mean? It means that the centralizer, so let's say G, centralizer with G is contained in some Levy L, where the L is still F, where the L is F7 Levy of an F7 body. G, I haven't finished the assumption. Okay, and for any time, what we have is in type G. Sorry, I haven't defined the exponent. Maybe I can do it now. It's got the at most f of the rank times 1 to the alpha. So what the alpha? When alpha is the maximum of the dimension of the class of U in L divided by the class of U in G, where U is unipotent. U is in, I think U is in L, and U is not 1. Okay, so it's the formulation of the theorem. So let me just give you 2 examples. What is the alpha here? So example G is SLN, value alpha is at naught, n plus 1 over n plus 2. And if your G is D8, value alpha is at naught, 17 over 29. Okay. Okay, and you can show that actually this is the bound, this term is very close to the next possible one. Okay. So let me just mention a few things about the proof of this term. There are B.
These questions are exponents and approximates.
No, it's some random numbers.
They're really random.
Yeah, I mean like we can compute it and it doesn't have any relation to the possible number.
Almost.
Yeah, 71. Like a 79. I don't know why. Okay. So how do you prove this theorem? Well, we started with something classic, which is the Harishana theory. And then suddenly we have to go to the derivative theory. And then some crucial result for us were the result of Lustig. Result on so-called hyperbolic support. But then we also need the dual version of the support, which is the notion of Kawanaga. On the generalized and fine Griess implementation and the so-called boyfriend set.
As an alternative to symmetric vowels, you can look at alternating vowels.
Oh, yes, yeah. So actually, you can look at all these relations.
Right.
And what we have to do is put in the bound that in the estimate that I give you, if you look at C lambda, where lambda is substitution, and then you put in the degree of the orientation corresponding to lambda. So you put in the lambda, chi lambda, and that's, so that will work here.
Oh, okay.
So it works for anything, for all these relations.
Is the alpha invariant that began the talk, does that also have analogs